Good evening, everyone. Thank you for joining us today. My name is Julia Doloff, and I'm a member of the UCSC Alumni Council and one of your Slugs and Steins volunteer organizers. With me is April Yee, another member of the Alumni Council and volunteer organizer. On behalf of the UCSC Alumni Association, we'd like to welcome you to our monthly speaker series, Slugs and Steins Lectures from UC Santa Cruz. Before we get started this evening, I would like to begin with UCSC's land acknowledgement. The land on which UC Santa Cruz is located is the unceded territory of the Awaswas-speaking Yupi tribe. The Ama Mutsun tribal band, comprised of the descendants of indigenous people taken to missions Santa Cruz and San Juan Bautista during Spanish colonization of the Central Coast, is today working hard to restore traditional stewardship practices on these lands and heal from historical trauma. As many of you know, our Slugs and Steins series engages a UCSC faculty member monthly with all of you, our alumni, friends, and family. We want it to feel just like you're back at UC Santa Cruz, sitting in class, but with a drink in your hand and without an exam. Before we introduce our speaker, we'd like to know where you're joining us from this evening, who you're watching with, and when you graduated. So please take a moment to fill out the short poll that should have appeared on your screen. And we will share the results with all of you when a majority of them are in. All right, so it looks like a lot of you are watching by yourself. Well, thank you so much again for coming tonight and joining us. We've got people from all over California, outer space, very cool. And we have people from almost every decade and almost every college. I represent College 9, and a couple Merrills, and not too many transfer students. Well, thank you for filling out that poll and joining us again. Tonight, Professor Andrew Fisher will explore how managed groundwater recharge works, why it matters, and how it can benefit communities, agriculture, ecosystems, and long-term water resilience. Tonight's talk will highlight emerging research on where and how recharge projects can succeed without causing unintended environmental impacts, along with a new incentive program designed to support landowners and tenants who help maintain these systems. If you have any questions throughout tonight's talk, please type them into the Q&A box at any time. If you see someone else's question that you like, you can always upvote it, and we will ask the question sooner. So Andrew Fisher is a distinguished professor of Earth and Planetary Sciences. He has been with UC Santa Cruz since 1995. Professor Fisher is an elected fellow of the Geological Society of America, the American Geophysical Union, and the American Association for the Advancement of Science. He has received two Excellence in Teaching Awards at UCSC, the Santa Cruz Nexties Brainwave Award in 2025 for research and public engagement on topics in water resources, and he will receive the Ed Ricketts Memorial Award for the Monterey Bay National Marine Sanctuary Research Advisory Panel in November. Congratulations. With that, I hope that all of you have your Steins, because I've got your slug, Professor Andrew Fisher.
Hello, can you hear me all right? Excellent. And we're going to get going. I only wish I could welcome you all to campus in person, but maybe another time. All right. There we are. And I think you should be able to see that.
Yes.
Wonderful. Well, I'm going to talk today about groundwater recharge and some opportunities to incentivize putting more water in the ground, and also some new work involving the reconfiguration of levees along the Pajaro River. And I want to just call out, there's a lot of people that have been involved in this work, many of them current or former students, grad students, undergrad students, postdocs, specialists at the university. So you'll see their names pop up periodically as we acknowledge their contributions to the information I'm going to present. And I really think it's California state law that if we talk about the water cycle, we have to show this figure. It really makes the point that water is in motion. We don't always notice that. We notice it when it's in motion in a rainstorm or runoff during a really big rainstorm or waves at the ocean, but we don't see the groundwater that's flowing beneath our feet throughout this region. But it's quite important. And the fact that it's in motion means that there are times we can figure out where it is and what it's doing. So we'll start with a few definitions. Groundwater, it's water below the Earth's surface. It fills pores that are saturated. Most groundwater actually just fills the tiny little gaps between grains of sand in most places. It doesn't include soil water that most plants depend on. That's shallower, and that's above what we call the water table. And mostly it doesn't occur in underground rivers, although as some of you know, we have underground rivers on campus. That's relatively rare. Most groundwater really is more like the diagram on the left. And when we talk about an aquifer, we mean a geologic unit that can both store water but also transmit it. And not all geologic formations can do both of those. So one of the tricks in finding and managing groundwater is to find units that have water and they can both hold on to it, but they can also release it and allow it to move. Another term that you may hear is groundwater overdraft. And this is where the pumpage of water out of the ground, along with whatever other flows may be occurring out of the ground, is greater than what's flowing in over a long period of time. And a consequence of this is that we can get many undesirable consequences. Two are shown here. The photos on the left are kind of famous images from the US Geological Survey, and they show in the Central Valley of California the effect of subsidence where the pressure has been lowered in an aquifer, and that aquifer has clay-rich units, and those units will compress and release water, and in doing so, the ground will sink. And this can cause all kinds of problems. Back in the mid-20th century, where the gentleman is standing there, the ground dropped more than 9 meters. But during the recent drought, there was also a return of subsidence in some parts of the San Joaquin Valley, and that's shown here with the USGS scientist holding the sign there. The other thing that can happen if you live near the ocean is too much pumping and other outflows can result in seawater moving in. And this is a big concern because just a tiny bit of seawater mixing with fresh water can make that water mostly unusable for people. And both of these two problems have a really long time scale for recovery, probably longer than a human time scale in both cases. So if we bring in too much seawater or we cause subsidence, then we're going to damage the resource in a big way. A lot of what I'll talk about today focuses on groundwater recharge, and that's where water at the Earth's surface sinks into the ground, typically through a process we call infiltration, and then reaches the water table, and then it can become groundwater. And recharge is the largest inflow term when we calculate a budget for an aquifer. It's influenced by all kinds of factors, including how we use the land, how quickly runoff occurs, and of course, climate. It's also one of the hardest flows to measure in that hydrologic cycle, arguably the only one you can't measure from space with a satellite. It can have a big impact on water quality, something I'm only going to touch on a little bit today. And importantly, it occurs naturally, but it can also be enhanced through activities that we'll describe. And right now in California, there's really 3 major threats that are impacting groundwater supplies. One of them is just demand, which typically either is steady or growing in different parts of the state. But the other 2 are kind of more cryptic. One is changes in land use, the addition of roads, pavement, rows in agricultural fields. These all tend to result in more runoff occurring. And when it rains and there's more runoff, then the water doesn't get a chance to sink into the ground. The other big change is more intense rainfall. And this is already happening right now. We see it in the record. It's not just a model prediction, but it's part of climate change. And even if we don't get less rain, if more of it happens more intensely, this also gives us more runoff. And that means we don't get as much water percolating into the ground. As we talk about water today, we're going to talk about units of acre feet. So that's an area of 200 by 200 feet and 1 foot deep. Think of it as a giant pizza box. It's easier to picture that amount of water than it is a third of a million gallons. I don't know what that looks like, but I can picture the big pizza box. It's about enough water for 2 households in California for a year. And when we talk about water, we're also going to talk about water years. And we're now in water year 26. It began last October, and it's going to end at the end of September this year. And we use water years in much of the Western US because we want to capture the period when most of the rainfall occurs, most of the precipitation, and we want to capture that each year within 1 year. So we don't split the rainy season between 2 years like we would with a calendar year. Yeah, I've been at UC Santa Cruz since 95, and when I arrived, soon after, the Department of Water Resources put out one of their 5-year updates on the water plan for the state, and they had some data which we collected and then made this plot. What it shows is in 1995, which was the last year of data when the report was put out, there was a budget for the amount of freshwater resources in the state of California. And they said at the time that there was 1.6 million acre feet of excess water use. All right. That's not the amount of water being used. That's the amount being used in excess of what could be sustained. And that was during a normal year, about 1.5 million acre feet of excess use of water. And during a dry year, this was about 5 million acre feet. And they projected in 1995 that by 2020, the normal year deficit would be almost driven to zero, and the dry year deficit would be cut in half. And this was in the same report. It was projected that the population of the state would go up by 50%, and that's equivalent to moving the entire population of the next 8 states all into California. So they projected that despite the increase in population, that the water deficit would be greatly reduced. Well, now we're living in the future, and we can kind of see how things have worked out since then. And it's not quite like the projection. Later reports separated a full water supply analysis and also a groundwater balance for the state. And you can see that this actually, the darker blue here, these are 2 wet years and 2 dry years. And then for groundwater, kind of alarming, even in the wet years, we have this deficit in groundwater. So things are not headed in the right direction in terms of our ability to manage the supply to meet our needs. And particularly in the case of groundwater, we have a pernicious and ongoing water deficit. I know we heard a lot about the drought 10 years ago, and it's interesting to look at around the state just how dry conditions were. This is data that the Department of Water Resources collects, and it's from 5 stations in the Sierra Nevada and mountains and the foothills here in the central part of the state. And you can see the peak drought years here. This plot shows the amount of cumulative water each year that fell as precipitation, and so the water year starts in October, and then it goes through the end of September the following year. And you can see from 2012 to 2015, things were dry. Overall, the rainfall was about half of what the average was in those 3 years. And that was a tough drought. It caused a lot of problems. It's been a little dry this year and the last couple of years. This is an update from Department of Water Resources. And here's last year, a little drier than normal, and then the current year a little drier than normal, or like at 88% or something. It also shows it's not nearly as bad as it was in 2021 or some of the worst droughts that we've had, where the water that fell in that area was less than half of what was normal. Also shown on here are some of the wettest conditions that have been observed, and this includes the big El Nino in 82, 83. If you're curious, for Santa Cruz, actually we're doing slightly better. We still rely on the San Lorenzo River for most of our water. The dash line here is the long-term average for the Loch Lomond Reservoir. And the rainfall this year is pretty close. We had basically 3 major events and then a few smaller ones. And it was a lot drier last year. So, overall, doing okay here in Santa Cruz. But I should note, many of you have heard about this big super El Nino that's coming, and it'll be interesting to see what happens during the winter of 82, 83, the last really large El Nino. Santa Cruz got 93 inches. That's way off this plot. And it was even higher than that in the San Lorenzo Valley. And of course, there was all kinds of flooding and landslides and problems with that. So I think we're all going to be keeping an eye on the weather this year. Going back to the drought about 10 years ago, this diagram shows water levels around wells through the Central Valley and other parts of the state. Here we are in Santa Cruz, right over here on the left. All of the dots that are red had at least 50 feet of decrease, and the dots that are orange had 10 to 50 feet of decrease. These are water levels that went down as aquifers were depleted. And you'll note that it's really all over the state. Of course, a lot of it is in the southern part of the San Joaquin Valley, but there's also a number of wells where water levels dropped in Southern California, and even some along the coast here where water levels went down. And there is an important connection between water supply and water quality. The diagram on the left here is a similar one showing changes in water levels, and the one on the right shows changes in or average concentrations of nitrate, nitrogen. This is a nutrient commonly used for fertilizer, but it can also come out of septic systems, landfills. There's some atmospheric deposition. Any number actually that's bigger than around 1 milligram per liter is going to have some human influence. But if you'll note the yellow and the red dots here, they tend to correspond to the same places where groundwater levels are down. These often go together because as aquifers get depleted, they tend to increase in the concentrations of solutes and nutrients, things that we don't want to have in the aquifer. DWR divides the state into hydrologic regions, and here in Santa Cruz, we're in the Central Coast region. And one of the characteristics of this region is that we satisfy our freshwater demand by a larger percentage of groundwater than any other part of the state. And so we don't use more water than other areas do. The Tulare Lake region and San Joaquin region use a lot more groundwater, but as a percent of demand, more of it comes from this area, comes from the ground in this area than any other part of the state. And that really is a challenge for us. During the drought, here's a quick update. Actually, 90% of our fresh water came out of the ground during the recent drought. Although the numbers are quite high in other areas too, in terms of absolute water use. It's just tremendous in the central and southern San Joaquin Valley. And the Central Coast is unique in that we're really off the grid in terms of this giant state water transfer and distribution system. The California Energy Commission noted some years ago that we use about 8 to 10% of the electricity in the state just moving water around. And that's really illustrated with this cartoon. And in the Central Coast, we really get nothing. This transfer, the San Felipe transfer hardly runs, and we're essentially on our own. We have no major rivers, no major reservoirs behind dams, no winter snowpack. So we're depending on groundwater, and of course here in Santa Cruz, we're depending on the annual rainfall. So some years ago, I started working on a series of projects that we bundle under this thing called the Recharge Initiative. It's me and colleagues and students and researchers and others who are interested in these problems. And we kind of have 4 major areas that we focus on, trying to map where recharge can be accomplished, where it can be improved, modeling the availability of stormwater, designing systems to help get more water in the ground and improve water quality, and then figure out how to monetize some of these activities to provide incentives. And tonight, I'm just going to touch on a few of these topics because we don't have a ton of time, but I'm certainly happy to answer questions about others and and follow up when we're done. This is a neat figure DWR put out a few years ago as they were embracing this concept of enhancing managed recharge around the state, and particularly through something known as floodmar, the idea that you could inundate large areas with flows from major rivers. When you have excess channel flows, you could spread them out over the landscape. But really, there's a lot of different ways to get water into the ground, and there's a lot of different water supply options. So what we're going to do is talk about two project examples, some work that we've been doing here that I think may be interesting, and give you a sense of what some of the opportunities are, both in this region, but also in other parts of the state and around the United States and around the world, really. There are many scales of managed recharge, and you're probably familiar with some of these. On the photo on the left, we see low impact development, and this is often set up close to areas where runoff is generated, like roads and parking lots and things. And it includes features like vegetated swales and infiltration galleries that can percolate that water locally. And at the other extreme, we've got large scale systems like they operate in Orange County and here in Santa Clara. And these collect surface water and then spread it over defined areas to percolate it into the ground. And these really differ in terms of scale. With LID, you're typically looking at a couple of acre feet per year through pervious pavement, vegetated swales, these kinds of things. Whereas with these big spreading grounds, there can be 100,000 acre feet or more put in the ground per year, but often through dozens of individual features. We've been working at kind of an intermediate scale where we're helping to collect stormwater runoff and then let gravity guide it to an infiltration basin in a location where it can infiltrate relatively quickly. Individual projects might get a few 100 acre feet or 100 acre feet per year per site, and then it can add up to something that's enough to make a difference. And one place we've been working is in the Pajaro Valley in southern Santa Cruz, northern Monterey counties. This is a special area. It's a very productive agricultural area. If it were a county, it would be the smallest in the state, but it would be number 5 in farm income. And that's because of a lot of really high value crops and berries, strawberries, caneberries, vegetables, all kinds of fruit, and about 30% of the crops are organic. Pajaro Valley was designated as a special act water district, and the Pajaro Valley Water Management Agency, or PV Water, was formed about 40 years ago. And that's because it was known this area was an overdraft. The overdraft here is around 12,000 acre feet per year. So they're working towards reducing demand and increasing supply in order to balance the basin. And we've been working at one site for a while now, and I want to tell you the story about this place. This is on an area called Boca Risa Ranch. It's in production of all kinds of vegetables. They rotate, of course, through different kinds of crops. It's often parts of this is in berries. The area is around 170 acres, and gravity drains runoff from this landscape. It's collected through a series of ditches. There's a small sediment detention basin, and then flows head here to the south and eventually into a 4-acre infiltration basin. The overall goal for the project here is to percolate about 100 acre feet a year or more into the ground in an average year. Here's what the site looks like. If you're looking to the south, here's what that 4-acre basin looks like. To the bottom here, we see when things are running, water is being directed in here through this ditch. We put out instruments to monitor rainfall. We monitor water level. We monitor the flow. We essentially try to calculate then how much water is going into the ground. In the spring, we go out and we pick up the instruments and download the data and process it. We also analyze for water quality. And this is just a quick look at the analysis. I'm not going to show you much data tonight, but here's just a couple of plots to give you a sense of what we deal with. This shows from October through June, so the first 9 months or so of water year 2019. This is rainfall on the top in centimeters per day. And then here's the stage or the water level at the inflow. So the inflow is pretty flashy. The water comes up and it goes back down again pretty quickly. On the bottom, we have here the infiltration rate into the ground. That's these lines on the bottom. And then the cumulative inflow that's occurred and net infiltration. We make a calculation to correct for water that would have gone in the ground anyhow, even if the system weren't there. And in this particular year, it was very average. We got about 107 acre feet of water. And that's water that would have run off into the Pajaro River when that river was running at capacity. So when it was providing little additional environmental benefit, the goal here is just to hold that water on the landscape, give it a chance to percolate in like it would have before that land had been developed, and improve conditions in the underlying aquifer system. And now we've been working out there for long enough. We actually just pulled our instruments for the 15th year of work there, and we haven't analyzed the data yet. But here's the last 14 years of data, and it's pretty interesting. This plot shows rainfall on the x-axis here in inches on the bottom and then centimeters on the top. And then the amount of runoff that came in, it's in acre feet on the left and cubic meters on the right. The overall project goal is the dotted gold line, and the average historic rainfall in the area is the dashed blue line here. And you can see the points are all over the place. One thing that's interesting is even with the same amount of precipitation, you can get wildly different amounts of runoff. And a lot of that is a function of just how intense the rain is and also how close together the storms are. If the rain is really light and it's spread out, we get less runoff. And if you look at this plot carefully, it's kind of interesting. Whoops, you can actually see two different trends. There's kind of a lower trend here and then a higher trend. And these are actually the differences when we have on the higher trend, that's when we get those years with the big atmospheric river storms, those big intense storms. 2023, the wettest year we've seen, was actually very much a normal year, just wetter. So the rain was spread out, but we get a new storm every 3 to 7 days, and just things kept flowing, but it really wasn't as much runoff as we might have gotten if that rain had been coming in these very intense short storms. So we'll see what happens this year. I wouldn't be surprised if we're somewhere up in that area for this project. So this kind of thing seems pretty straightforward, and you might wonder, how come we don't do this a lot more? How come these aren't all over the place? And there's a lot of challenges with collecting stormwater in this way. It is relatively inexpensive and straightforward to do, but in an area where there's really high value agriculture, it means having some land that's either taken out of production or not used for other purposes on these working lands. There's also maintenance that's involved. This land belongs to private landowners, and they need to take care of collecting sediment that collects. There's also debris of various kinds that has to be cleared away. So this is actually effort that has to be put in. And pretty much any system that you run, whether it's basins like this, or it's percolating wells, dry wells, or it's even floodmar across fields, there's going to be impacts. And one of the challenges, a lot of times folks would like to do projects like this, but they don't want to take on the burden of those costs. And we have a model for dealing with this, and it's something that was developed in the energy sector known as net energy metering. And the concept here is that you could put up a series of solar panels up on your roof, and you could generate power, which you could use. And if you had extra power, it could go back on the grid. And back before we had smart meters, you could actually go outside and watch your power meter run backwards. So, and in essence, what was happening here was that PG&E was paying 100%, 100 cents on the dollar for the cost of that power. We could talk about that later, whether that was a really good idea, but that's what they were doing. And what this all requires really is you have the ability to measure it, like this meter. You can do an accounting. You have some kind of a formula to calculate a benefit and a rebate. And then the folks who are participating and the agencies involved and so forth have to trust each other. And that's actually kind of a big one. So here's how this can work. Imagine that there is a ranch and they have 75 irrigated acres growing these delicious red berries. These berries take a lot of water, about 2.5 feet. So this is going to be around 188 acre feet for this farm every year. But the rainfall here is only about 1.5 feet. So of course they have to pump groundwater. And we're going to assume a certain amount of runoff here. And that's actually a value that's pretty typical of what we've seen on our developed sites. So imagine 3 different ranches. The ranch has 75 acres in production, but it also receives runoff from the surrounding landscape. So imagine the runoff is from 200 or 400 or 600 acres. And imagine that we set aside 1% of that area for infiltration. In the Pajaro Valley, pumpers pay what's called an augmentation fee or a pumping fee for pumping groundwater. And it's relatively high compared to much of California. It's currently around $325 an acre foot. So imagine that through net metering, we have a rebate of 50% of the net infiltration. So here's how that can pencil out. We have 4 scenarios here. On the left, we have a grower that's not participating. They just pump 188 acre feet. And then on the right, we see 3 different scenarios for growers who participate in the program. One with drainage of 200 acres, then 400, 600 acres. So for the grower whose property drains 200 acres, they actually collect around 120 acre feet of runoff, which is percolated in the ground. So their net removal of water is only 61 acre feet. By the time we get to drainage areas of 400 and 600 acres, you actually have net negative pumping because more water is put in the ground than is taken out to grow the berries. So larger drainage generates more benefit. We're actually operating a program like this in the Pajaro Valley, and my group works with the Resource Conservation District of Santa Cruz County as a third-party certifier to help make these measurements to figure out how much water goes in the ground. And part of the way this works is that we have an agreement with our participants that the agency and the landowners aren't going to quibble with our numbers. We do the math, we make the measurements, and then we figure out how much water goes in the ground. The benefit for the participants is that for the grower that doesn't participate, they're going to pay about $60,000 in pumping fees for water. But for the participant whose property drains 200 acres, they get a rebate of around 20 grand. So their water cost has dropped to about $40,000. And by the time you get up to this grower whose property drains 600 acres, they grow the delicious red berries. They pump the water they need, and at the end of the year, they get a check for $1,000. So the better the system works, the more the rebate is, and that's an incentive for the participants to maintain their system. The rebate is not intended to cover the value of the water. It's actually intended to offset the costs for the participant because of the loss of use of land, the high land values, and then for the maintenance that's needed. And because under this scheme, the rebate is pegged at 50% of the water cost, it can actually make money for the agency. Unlike net energy metering, which costs PG&E a lot of money and caused them to cut back on the program, by setting the rebate at less than the full value of the water, they're able to actually make it pay. So we actually have a program like this. As far as we know, it's the only one of its kind in the United States. I heard there was something like it in Australia, but I've never been able to find information on it. Our overall goal is to get 1,000 acre feet per year in the ground. We're not there yet, but we're working towards that. We work with the RCD, the Resource Conservation District of Santa Cruz, and we are the third-party certifier for the program. We help to identify the sites, we fundraise, we develop plans, and we build these systems to be measured. We work with landowners and tenants to validate, certify performance, and then we write up a report. And then the agency, in this case, Pajaro Valley Water, they cut a check for the landowner. We currently have 3 operating systems in the Pajaro Valley. We're in the process of developing another one. They're at 65% design right now, so that means they can finish the permitting, and we still hope to go into construction this year, but it's looking pretty tough given the timing right now. And of course, we have other sites we're looking at, and we're talking to other parts of the state, other water agencies, to see if it's something they may want to look at and potentially adapt for their area. A group of us published a paper a couple of years ago that compared the cost of recharge net metering to other alternatives like those that are listed in the groundwater sustainability plan for the Pajaro Valley. And in general, the unit cost for net metering is less than the unit cost for the alternatives that the agency will be looking towards in coming years. We also compare these to some of those in the Salinas Valley, and that's one of the groups that we're in discussion with about perhaps trying to develop a program like this. You may have heard of water banking, and that's not what this is. I actually am not a big fan of the term water banking. I think it confuses people. water keeps moving, even when it's put in the ground in an aquifer. And so I don't really think that an aquifer is very much like a bank. Um, but it's different in other ways that are really important. It recognizes the hydrologic system services that are generated by infiltration as a process. So that's what we measure, and that's what we peg the rebate to. It's a rebate paid on pumping fees as opposed to just a cash payment, but in fact, it could be configured in different ways. The system is structured so that it encourages maintenance of the systems. The better they perform, the more water goes in the ground and the bigger a rebate check that landowner or tenant is going to get. And it creates non-extractive co-benefits because we're not claiming that every acre foot of water that goes in can then be recovered later on. Different areas, different basins may need different configurations of a program like this, but I actually think it's quite important to think about opportunities of this kind and different ways we can incentivize the enhancement of groundwater recharge. And what I'm going to do now is make a hard pivot to a somewhat related project. It's in the same area, and it's also focused in part on increasing groundwater recharge, but it's kind of a new area for me and my group, and I'm excited about it. And I'm going to wrap up by telling you a little bit about this. This is a project where the levees along the Pajaro River and two of its tributaries, Corralitos Creek and Salsapuedes Creek here, new levees are going to be put up, old levees are going to be moved out, reconfigured. And this is a big project being undertaken by the Army Corps of Engineers and funded in part by the state of California. And we were brought in with a big group to try to figure out how to get more benefits out of this project. So we're doing this work in support of flood risk reduction, flood risk management, but it's also to get additional benefits. Some of you might know much of the Pajaro Valley is currently a floodplain. And in fact, it used to be a vast wetland complex. 100,000 years ago, when sea level was about 20 feet higher than it is now, and the ground was a bit lower, this whole valley was inundated. It was a vast wetland complex. And, you know, natural rivers, they tend to flood pretty frequently. The natural levees that form, they do so typically such that rivers flood about every couple of years. So here we have a very productive area. We have a lot of people and a lot of activities going on close to the river. The Pajaro River flooded many times in the 1800s and 1940s when people were out here and realized what a productive area it was. And levees were put up along the river first by the U.S. Army Corps of Engineers back in 1949. The general intent was to provide 100-year flood capacity. That means that an event that statistically would occur once every 100 years would stay behind the levees, would just meet the levee capacity. But in fact, there were major floods soon after that flooded large parts of the valley, including 95, the year I arrived, 98. And there's been a plan to improve the levees that goes all the way back to the 1960s, but it could not get approved until in 2020, 2021, finally, the feds and the state were able to get together and line up sufficient support. And the Pajaro Regional Flood Management Agency was formed to oversee this project, which incorporates parts of two different counties. So they're an agency that was created really for the purpose of seeing this project through. And they were just getting on their feet and getting started. And then we had levee breach and levee bypassing in 2023. That was that big water year I pointed out before. And here are some sad photos from upstream on the Pajaro River. This is on the Monterey side. And then downstream, the community of Pajaro was inundated. And it was no one lost their lives, but people were injured and farms and businesses were damaged. It was a really costly flood. And this wasn't even a 100-year storm. It's been estimated that the Army Corps has estimated that right now the levees are kind of 8-year levees. So, you know, this is a project that's really, really needed for this area. And I'm glad it's happening, and I'm excited that we can contribute to some of the work. So our part of the project with others, I'll tell you about them in a minute, is really to look at, here's an area where levees are going to be changed. What can be done to increase groundwater recharge, improve water quality, and enhance habitat, while also reducing the risk of flooding. Here's where the levee breach was in 2023, and here's an area where there was no levee and water came out and flooded this area here off of Corralitos and Salsa Puedes Creek. So the goals of this project, which was funded through the University of California, they received an allocation of funding for climate action projects back in 2023, and we applied for some of that and were successful. So the goal is to gather data that can be used for the flood risk management project to improve channel capacity, but also evaluate current conditions and find out where is recharge occurring through the bottom of the river. What are the impacts of water quality in water, particularly that goes in and out of the stream bed? And where are hotspots for habitat, either endemic species or invasive species? And then provide actionable information to the Army Corps and PERFMA so that they can make plans that'll achieve additional benefits beyond just improving flood risk reduction, which is a big goal, make no mistake, but we think we can get some other goals at the same time. And in doing this, then increase capacity within the area to then manage that system. Because the feds and the state are going to pay for this capital project, but the responsibility for maintenance is going to be on the locals. So the concept is kind of like this with traditional levees. You have kind of a narrow channel, and that can be challenging when you get high flows. You can have damage to the levees. You don't have as much capacity. Whereas if you can move the levees out and incorporate complexity within the levee system, then you can encourage more improvement. So when the call for proposals came out, it was a big rush, right? Very early in 2023, a group of us got together. I'd actually been talking with the director of PERFMA for a while, looking for opportunities when this call came out. So we got with the Resource Conservation District and colleagues at UC Berkeley, UC Davis, and Cal State Monterey Bay. And also DWR is one of our end user co-PIs for this as well, because they have interest in groundwater recharge. So it's really a great team working towards figuring out what's going on here. And the thinking behind this is we know upstream of this area on the river, the Pajaro River loses quite a bit of water, but this downstream area we didn't really know. You can have streams that gain groundwater, we call that base flow. You can have streams that lose water to groundwater, and that can be a form of recharge. You can also have disconnected streams where groundwater levels are so far down that they lose that direct connection, or maybe there's no recharge because there's no flow. And these can change. They can change with time, and they can vary as you move up and down a stream or a river. So a big part of what we're trying to figure out in this project is where does the Pajaro River gain water, lose water, or just exchange water with the subsurface? And I'm only going to have time to show you a little bit of information, but I'm going to focus on this one section of the river. It's called Reach 4 of the Pajaro River. So we're going to zoom in on that box right now. And what we did when the project started was set up a whole bunch of stream gauges to measure discharge where the blue dots are located. And we also had set up sample sites where the blue dots are and the green dots. I'll point out that the old channel of the river used to go where this red dashed line is. You know, rivers are dynamic, they change, and there's also tributaries. There's a tributary that came in here, there's a tributary that came in here, and so there's lots of old channels that are buried. And part of what we're trying to do is figure out where they're located and where the river might be able to connect to them. So we've been doing a lot of measurement, instrument deployments, sampling, analysis, and then surveying of various kinds. As I said, I'm only going to get a chance to tell you one part of this, but it's something that's really cool and I'm excited about it. So one of the things we did is install these pressure gauge systems in the bed of the river. And so these systems have two gauges, one pressure gauge that's measuring the pressure in the river bed down here, and another that's measuring pressure in the river. And by measuring the difference in pressure, we can figure out which way water may be flowing, either up out of the ground or down into the stream bed. And then we also have temperature probes that we build, and we hammer these into the river, and they've got two temperature sensors that are below the riverbed. And by measuring temperature, we can use heat as a tracer to figure out whether water's flowing up or down and how quickly. And we pulled in a bunch of gear last year, and I've got an amazing new grad student. Well, not new now, I guess he's been around 2.5 years, Ethan Yen, fantastic. And he did these analyses and pulled this together. And I want to show you this animation because I think it's really pretty amazing. So the diagram here, you're going to see what we call the stage. That's the height of water in the river. So here's early in the water year, and then later in the year. Here's a big storm we had. 2025 wasn't a super wet year. We had one big event and a couple of smaller events, right? So you're going to watch this ball. It's going to move through here. And at different stations, these arrows are going to move, and they indicate whether the flow is up or down. Downward flow will be blue. Upward flow will be red. You're going to see one measurement a day, and the longer and darker the arrows are, the greater the flow rate. So let's watch this. And I encourage you to start here, watch this area, and I'll show the little animation again in a minute. So that downward flow is from five different sensor systems here, measuring the downflow in that area. It's pretty strong. It actually slows down downstream from there, but that area pretty much always loses water. Whenever we measured flow there, we pretty much always saw downflow, and sometimes it was as fast as a meter a day, which is really, really fast. Okay, so that's that area. But now I want you to look over at this area, and this is an area where there's been different incoming channels. There's a tributary here and another one that comes in there. Let's watch this again and watch these arrows in this area. And what you'll see is significant downflow and in some areas upflow. And the upflow is mainly here, and you'll see some downflow in this intermediate section, particularly now, right? So we're seeing big differences in the flow rate. We actually get really high downflow here, but late in the water year, when there's not much flow in the channel and when sediment has collected on that part of the channel. So we think that as part of the levee realignment, which is going to be looking at modifications to this section, designing some of that in order to enhance recharge should be quite beneficial for the area. So that's part of the report we're writing up now. We're just pulling more instruments in. This project is still underway, but this is just one of the cool products that we've generated from that. So I'm going to wrap up now. I'll just say that enhancing recharge is really important. We have to do it. You know, some of the models predict we're going to lose all of the Sierra Nevada snowpack by 2021, or 2100 rather, not 2100. It'll be either greatly reduced or gone, and that's as much water as behind all the dams in the state. So, you know, we're losing storage, and the best opportunity is to get some of that water into the ground. But to do that, we've got to find the right places where the water can be added safely and quickly. And we need to look at ways to improve water quality. I didn't talk about that today just for lack of time, but I'm happy to answer questions about it. And we need to design these systems so we can measure how they work, because we need to learn how to do this better. And that's been one of the things we've really worked on a lot over the last decade and a half or so. And these levee setbacks, the Pajaro River is not the only river that's being adapted for a changing world. You know, all the infrastructure, whether it's levees or storm drains or culverts, ditches along roads, they're all too small because they're based on looking back over 50 or 60 or 100 years at what the weather and the climate and the runoff used to be like. And as we look at the way the climate is now and the hydrology is now, these systems aren't big enough. They need to be reconfigured, and that's an opportunity because we can get other benefits along with managing these systems to reduce flood risk. And we can do this by working together. And I've really learned that in these projects, and particularly with the recharge net metering project, and then more recently with the levee project. Multidisciplinary teams and working with the state, with the feds, with local heroes, it really helps. And we get a lot of good knowledge for doing that. So more recharge is coming, and we need to do this. As I wrap up, I just want to acknowledge again all the folks who have participated to these studies. It's just been literally dozens of field hands and helpers and senior theses and master's degrees and PhDs and postdocs and all these other folks who have helped out on these projects over time, just a cycle of people. And it's been amazing. Really great group, and I'm just so grateful for those opportunities. So with that, I want to thank you for being here, for being interested, and I'm looking forward to answering your questions. You'll find some information at this website. You can type in rechargeinitiative.org. It'll bounce you to my UCSC site. It'll redirect you to the Recharge Initiative page. You're also welcome to reach out to me directly. I have reprints of papers, and I'm happy to answer questions that you might have. So thank you. Thank you very much.
Thank you so much. So first, Joe would like to say that you are a superbly good presenter, teacher, and advocate, and they thank you for being part of the solution.
Oh.
So our first question is from Benjamin, and Benjamin asks, are there meaningful recharge opportunities for the Santa Margarita Aquifer?
Yes, I think there are. I haven't worked with folks in the San Lorenzo Valley and Scotts Valley in some time. We did a mapping project a few years ago looking at MAR suitability in Scotts Valley and the San Lorenzo Valley, and we identified some sites that look promising. One of the big challenges in that area has to do with getting an adequate supply of water directed to those sites when it's available. Personally, I think it would be wonderful if the city of Santa Cruz and those communities could have an agreement. Santa Cruz is working on one with Soquel Creek where they can do a conjunctive use and move water between the areas. That would really be phenomenal if the San Lorenzo Valley, Scotts Valley were linked to all of that. So during high flow periods, you'd be able to take excess off of the river, recharge it. During drought periods, you then have more water in the aquifer that could be shared. Santa Cruz doesn't have the benefit of a lot of groundwater resources. Soquel Creek depends on groundwater, but their aquifer is relatively tight, so they need to inject that water. I think up in the Santa Margarita aquifer areas, there probably are opportunities, but there's a lot to be worked out in terms of the rights to the water, the ability to, share water. But I do think there are opportunities from a physical perspective in terms of what's possible to get in the ground.
Thank you for that. So Ahmed has a question. Do we run into issues of water rights and how to deal with it?
Yes, we do. Although it's been really interesting, as part of the net metering program, we specifically target areas that don't have blue line streams. This is hill slope runoff as opposed to diverting water out of a river. That can be done, but the water rights challenges are significant. The state board relatively recently enacted a streamlined process for a 5-year rights permit as a temporary permit. I think it's still onerous and it's challenging for projects of this size. It's also challenging that you have to keep renewing it. And, a lot of times the agencies just don't have the staff or the funding that they can keep up with that. So, if you're a large agency, you may have the bandwidth for that. You may have the funding for that. But for smaller agencies, it doesn't make a whole lot of sense. I'll tell you that we consulted through these projects with a number of water rights attorneys, and they were split. They have been split on whether, in fact, a right is required for this work. The short answer is it depends, most likely. And sort of the most coherent recommendation that we got from one of those attorneys was we don't need a right, but we should apply anyway. So it's pretty interesting to be in that area. It's not an area where I have expertise, so I really defer in many cases to the experts, but we are working on those issues with Pajaro Valley and with other water agencies with which we've consulted, and that is an issue that they do have to address ultimately.
Great. Joe asks, what is the source of the rebate checks that are issued?
The rebate checks are issued on the pumping fees. So in the Pajaro Valley, if you have a well on your property and you pump out, say, 10 acre feet, and the pumping fee is $325, then you're going to pay $3,250 for that 10 acre feet of water. It's your well, it's your electricity, it's your pump, but the agency as a special act district is allowed to charge that fee on the water that you pump and then they use those fees to run programs. And some of the programs they run are things like water conservation. They've got a new project that they've recently constructed at College Lake where they're recycling runoff there and then distributing it through a pipeline. So they run a whole variety of programs. They also need to pay for the well metering itself. So folks who pump then pay a fee. And if you participate in the program, then you're able to get some of that money back, right? You pay your fee, and then at the end of the water year, when our report goes in, the agency cuts them a check and sends them the rebate. So they're really giving them their money, part of their money back is what's happening there.
All right. Emily asks, given the high agricultural use in the areas of study, is ag pollution being considered for the new levees and infiltration enhancement? If so, will there be mitigation strategies, for example, water treatment, placement, et cetera, in place?
Yeah, great question. So let me answer that in two parts, because one part is for the recharge projects and the other is for the river. And the short answer is yes to both. For the recharge projects, one of the things I didn't get to put in, I just didn't have time tonight, but we've been experimenting with adding bioavailable carbon to the soils at the bottom of these basins. And we've done field experiments, plot size experiments, and operational scale experiments. And then we've also done lab experiments with columns where we collect intact columns, bring them into the lab, push water through them, and we look at different carbon additions. So we're looking at things like wood chips, aged wood mulch, almond shells, other materials. And indeed, we can accomplish significant water quality improvement, water quality enhancement. What happens is that the bioavailable carbon stimulates soil microbes. They use up the oxygen, they switch to another oxidant, nitrate, and they consume that. In some of our experiments, we get 100% removal. We've not seen that in the field, but we also sample, along with Pajaro Valley water, we sample shallow groundwater wells in that area, and the water we're putting in is better in quality than the ambient groundwater. So we are moving the needle in the right direction. Not only are we not doing harm, we're actually improving groundwater quality through this process. And these systems are monitored. We collect samples, we take them to an EPA certified lab and get them analyzed. So we are concerned with that. It is an ag intensive area, but particularly after the first flush of the season, just the first bit of runoff for the season, the water quality is pretty good. The main issues we have to deal with are sediment, and that's a challenge, but our system tends to trap that. Very quickly, for the river, the Pajaro River is considered to be impaired by the US EPA by nutrients. So the water comes into the basin from higher up in the Santa Clara Valley, from San Benito County. That water arrives with relatively high nitrate concentrations already. And part of what we're trying to figure out is what could be done that would allow the river to do a better job of denitrifying, of removing that nitrate. In an earlier study, we saw that upstream where there was a lot of surface water groundwater interaction, where the water goes in and out of the stream bed. That creates an environment that's very conducive for microbes in the stream bed to consume that nitrate. But that process seems to stop as we go downstream. And in another part of the work we've been doing, we've been sampling sediment on the bottom of the stream. And that part of the river collects a lot of fine sediment. So one of the things we're proposing as part of our report to PERFMA and the Army Corps is that they build some structures upstream that'll help to collect some of that excess sediment. The river is also impaired with sediment that comes from higher in the basin. We think if we can hold that back, then it'll mean downstream we're going to get more surface water groundwater, and that'll allow the removal of the nutrients. And then when the big storms come in the winter, that plug of sediment can get blown out and into the bay like it is anyway. So we're not trying to collect and haul out all the sediment. That could be done, but that would be pretty expensive and challenging. Instead, we're trying to figure out how to get the river to operate better as it already does, and just give that water more of a chance for the nutrients to be consumed. So we're hopeful. And what's exciting about this is we have the before data. And so after the new levees are put in, folks can measure what happens, and we'll be able to see whether there actually is the improvement. And that's why we need projects like this, because the thing that's going to convince people is the results. I can talk, I can do models, but none of that is going to convince anybody. They want to see the results. And it's rare to get a chance to do this level of analysis and then put the new levees in. and then see what happens to the river. So we're super excited about that.
Fantastic.
Awesome.
Thank you. So Christine's question is, in designing these recharge basins or systems on farms, are there some cultural practices that might prevent nitrogen from leaching?
Cultural practices. I wonder if you mean like activities, like farm activities that might create a limitation of some kind. Not that we've seen, but honestly, we've only done this in a few places. There's all different forms of agriculture, all different. So here's an example. Yeah, okay, I thought of one. If you had a farm that used a lot of manure, that probably it would provide carbon, but manure or compost, as another example, those are also really rich in nitrogen. And so I don't think it would do much to improve water quality because it wouldn't provide as much stimulation for the microbes to consume the nitrate, for example. They'd have a bunch of carbon in the compost or the manure, but they'd also have a bunch of nitrogen. And so probably that would just be like more conventional ag runoff, and you wouldn't get as much processing. So that might be an example. That isn't done very much here in the Pajaro Valley. But this is a reason why, in order for ideas like this to spread and to be used in other places, they're going to have to be set up correctly for those areas, for the kind of ag they do, for the economy, for the practices that are used. And we need locals who understand those systems and how they're run. The partners, the landowners, the growers, they know how their fields work. They know when they get more or less runoff in different areas. So that partnership is really important in order to figure out how to do it well if there are different practices that are being used. Yeah,
All
good
right.
question.
Yeah. And another question from Christine. Since when you alter the land so intensely, how difficult is the environmental review process?
So this is a really nice part here in California. Agricultural landowners, they are able to manipulate the landscape as part of their operation. So when you work on working lands, on a ranch, on a farm, not only do you have experts who know how to move soil, like this is what they do for a living, and they have equipment, and they have talented farm hands, the folks who drive that equipment and know how to move things around. But they also, a project like this, it does have to go through a review, but that review is really minor compared to what you would have to do if you put it somewhere else. So, we're not limited to doing this on farmland. This could be in different parts of the landscape. It could be on parks. It could be in, other land uses. But working in a farmed landscape is actually kind of advantageous in terms of getting these things approved because of what's already being done on those lands.
Thank you. David asks, is it possible to recharge with gray water so households that depend on well water could offset some of their use?
Yeah, that's a really good question, and I would lean against it. Gray water is for folks who don't have those systems. This is, where you have plumbing in a house so that water from a sink, water from a shower can be collected instead of going into your sewer. It can then be reused. Water from a dishwasher, from a washing machine, not sewage, not water from a toilet, but other water. They call that gray water. One would have to be careful. That the challenge is that there is a lot of household chemicals that are used incidentally that are not ideal. The other big issue I'd wonder about, it's a little bit like low impact development. I'm not sure there'd be enough water to make it worthwhile. These projects are in general designed for 100 acre feet per year on average. So that's like that's the entire water use of 200 families per year. That's kind of our goal. So if you could do this at a small scale in your yard, I've got a rain garden in my yard, and we direct some of the runoff from the roof just into that rain garden. It's got gravel and it percolates a little bit. That kind of thing makes total sense. But if you have an aquifer that people use for drinking water, you've got to be really careful. And you really want to have some travel time for that. In principle, you could, but I would be a little nervous about what else, what's coming off the roof tiles, what's coming off the some of the cleaners that are being used, that kind of thing. I think you'd have to be very careful about the quality of that water.
Thinking of PFAS, even microplastics.
Yeah, right. Exactly. Like there's all of these which we didn't even think about very much 10 years ago, and now they're kind of popping up everywhere. The water repellents and the microplastics. People are finding those just everywhere. And I was at a conference a few years ago, and folks were using something called a tomatillo virus. It's not a virus that makes people sick, but it's one that a lot of people have, and so you can see human effects in groundwater by looking for that virus. It's just like a marker. And the fact that we see that in groundwater all over the place is an indicator that we're already impacting groundwater, right? And so I think what it really takes is a careful look. What are the groundwater conditions? What are the problems? If you have a gray water system, maybe sample it for a while, find out what's there, get some tests run for a couple of weeks, like gain confidence, move slowly. Because I think it might be possible, but yeah, whenever there's people around, we tend to have an impact on our environment. Hard to avoid.
Yep. This is a funding question. Celia asks, have you approached San Jose Water Company for funding assistance?
So we did a project that was what they call a pre-feasibility study for Santa Clara Valley Water a couple of years ago. We did a suitability analysis of the region, and also working with our colleagues at Berkeley in a institutional analysis. We think they have potential. They do a lot of recharge already. If you drive over 17, you go by Lexington Reservoir, and as you're headed to the airport, for example, from Santa Cruz, all of that water goes down into a canal and it gets used for recharge. They have dozens of recharge basins there already. But we were trying to talk with them about other opportunities, particularly in the southern part of their service area. I think the hangups often are more in the realm of legal. In that case, there were concerns if they picked one area that another landowner might be angry that they weren't picked. It was a lot of issues that really didn't have to do with whether it was physically possible or whether the quality was good enough. It was more about how people would respond to it. And so I think it's been a learning experience in a lot of ways. We imagined at first when we went over there that a big agency with a lot of resources, they'd be into this. This was something they could do right away. And it turns out a big agency like that also has lots of constituents with lots of ideas, and they're just very cautious. And I think that's, for good reason. They've learned through the years. We're very fortunate Pajaro Valley was willing to take a chance and let us try this. When we first launched it, it was a 5-year pilot, and we weren't sure if we'd be able to do it. And they were willing, their board of directors was willing to let us try. But we're hoping that over time, as we show these results, other folks will be interested and willing to give it a shot. San Jose wouldn't really be much interested in supporting us here, but maybe they'd be interested in supporting us or another partner there. And that's part of what we'd like to see happen. We're currently working with the Resource Conservation District to get the word out and try to encourage others who might be interested to look at this. And we're putting together, we have a cost benefit tool that's being built, and we have kind of a manual we're working on how to do this. And so that's our goal, is not to go out and do it ourselves, but to try to encourage folks to look at it and see if it might work, maybe with some modifications.
Thank you. So our next question is from David. David asks, says there's a lot of concern about water use in data centers. Is there a way to recharge to mitigate their water use? And then a similar question is from Van about whether you've had any interest in these projects from the tech industry.
I'll mention the second one first. We've had a few contacts from venture capitalists who want to figure out a way to monetize it in terms of return on investment, and we've tended to hold them off. We think there's a lot of challenges here making the economics pencil out when we're not trying to generate a profit. So that's part of this that I do have some concern about. I think there's some tension about how much that rebate should be. what the costs are. I mean, all of these water projects cost something. The world of free water is gone, and I think so. That's a concern. I'd say in terms of the data centers, I think it's a concern for sure, like it is for any major industrial user. And to draw an analogy, during the hydrofracturing boom, the fracking boom about 10 years ago, there was a lot of concern about negative impacts on groundwater. And there were a few cases where, because of unusual conditions, gas got into an aquifer, and you saw photos of like a spigot with a flame coming out of it or something like that. Really, the biggest harm is just any industrial process, right? The biggest risk from fracking wasn't contaminating an aquifer. It was just all the truck traffic. It was all the incidental spillage you get every time a tanker hooks up to a tank and then disconnects again. You spill a little bit on the ground. It was all the dust being kicked up. It was all the incidental, just industry suddenly in people's backyards. But everybody was focused on, oh my gosh, they're going to destroy the aquifer. Again, it's not that it can't happen. It's just like, to me, the big problem is just right in front of our faces. As far as the data centers go, yeah, they use a lot of water. It's a small fraction of the amount of water we're using now for other things. So at some point, that's going to be an issue. But I don't think we should be distracted. I think that the power use in general is the big issue. How much of our energy grid are we willing to dedicate to that activity, and is it really worth it? I think there's good questions about water also, but it's just, I've seen some numbers, and even with build out of some of these centers, you're looking at less than 1% of water use. I've not vetted those numbers myself, but I've talked to folks who have looked into that. So at least at this point, I think, but let me be clear, that could still be a whopping effect on a community, right? Let's be clear, right? This happened with like the boom in wine grapes, where wineries went in and wells went down, and all of a sudden homeowners, their wells went dry. Like, again, you don't have to use 30% of the water of the state before it's a problem for a community, right? So 100%, absolutely. And folks who are faced with that, I hope they have the opportunity to learn about what the impacts will be if it goes in, and then communicate with their elected officials and others to express themselves. I mean, that's just critical. So I know community by community, this is a huge issue. Statewide, not yet. It's not as big, but absolutely at a local scale, yeah, this could be huge. You could certainly have aquifers depleted in individual areas by clusters of data centers.
Got it. Another question from David. For the Pajaro River project, would it make sense to pump water from the river to the banks within the widened levees, not just wait for the river to overflow?
That's a good question, and my general response is we want to just use gravity as much as we can and just use the design. So part of what we're looking at in design is two general types. One is called side channels, where you have the main channel of the river, and then you've got little side channels that go out onto the floodplain. And then what's called terracing, where you have different levels inside the levee. So the levees are moved out, but then the channel's in the middle, and then between the channel and the levee, you've got these terraces. And what you do is you design them so they get overtopped relatively more frequently. So for example, there might be a 2-year terrace and a 4-year terrace and an 8-year terrace and a 12-year terrace, something like that. And then within those, you could have these side channels. One big question is how much work it's going to be to maintain those, because if there's not some maintenance done, the vegetation is going to come in, a lot of invasive species, that's going to trap sediment, and we'll kind of be back where we are. So this is another issue. You want, whatever those structures are, you want them to be accessible. You need ramps, you need access roads, you need staging areas for people and equipment and supplies, so that there can be regular maintenance that's not too expensive to keep them functioning. And I think that's probably the best way that these can operate for the long term. If we start putting in things like pumps and pipes and so forth, that's just more infrastructure that's going to be in harm's way. When this river flows at high levels, you don't want a bunch of obstructions inside those channels, and you don't want to be penetrating the levee with a bunch of pipes. So you really want the levees to be strong, but just put back so more of the floodplain is next to the river.
Got it.
Great.
These are good questions.
Yeah.
Yeah. Okay, so we do have a question about desalinization, and is that an option? Is desalinization Año Nuevo an option in Santa Cruz County?
Desalinization is an option in general for urban areas. And that's mainly because urban water users pay a lot more than rural users and ag users for their water. And the cost of desalinization is high because of the infrastructure and then because of the energy that's required to basically push the water through filters, through very, very fine filters. And that's just physics. It's a really hard thing to overcome. And the same thing applies for potable reuse, like they do in Orange County and like they're doing up here at Soquel Creek. That's essentially a desalinization style process. After the coarser materials are removed, the water has to be treated to a very, very high level. And it's just energy intensive. So you're looking at typical values or costs are like $3,000, $5,000 an acre foot. It's just a lot of money. And I'll tell you that, Pajaro Valley, that water cost is relatively high. During the drought, when there were water auctions, water was going for $1,000 an acre foot in parts of the valley. So that happens when there's a drought. But like year in, year out, 300 an acre foot's a lot. And so that's the challenge for an ag area is even for strawberries, I don't think you could afford it. It's just too expensive. Now, what do you get with desal? What's the big benefit? The big benefit is you throw the switch and you know how much water you're going to get. Like it's predictable. One of the other challenges for these systems, we know over time they can perform, but they might not perform every year. And I cannot tell you how they're going to perform. I can't tell you this year whether it's going to rain hard or not. Some El Niños, it doesn't. And so, the big benefit with desal and with potable reuse is the predictability. The fact that you sort of throw the switch, you can get a certain amount, middle of the night, middle of the day, weekend, weekday, rainy, sunny, you're going to get some water. But the costs are high. And of course, with desal or water treatment, you still have to dispose of the residue, whatever the salt or the other materials you hold back, you've got to dispose of those. So all of these things are real costs.
Mm. All right. Emily says, what are the concerns for levee management given the various flow styles of rivers?
That's a great question. So I'm going to say that when we started this work, I'd read a little bit, but this is the first project I've worked on involving levees. And we've been talking with the Flood Management Agency and colleagues with the Army Corps of Engineers who are experts on this. One of the things they're looking at here, and one of the things that may determine how far out the levees go, is whether there are old channels in the floodplain. Old channels that are coarse material, that could allow water to underpass the levees, and that would cause problems. So that's an issue. Another issue is the maintenance, just keeping the levees in good condition. They're typically designed so that there's a road on top. It's not for regular traffic, but it's for maintenance and for accessibility. And it often involves being careful. You want some vegetation can help, but you don't want it to get too rough. And you don't want vegetation that's going to break up the levee material. It's made of earth, essentially, along with other materials. So that's going to be something that the Flood Management Agency, PERFMA, will be putting together essentially a maintenance book. And then they'll be working with the two counties, with Santa Cruz County and Monterey County, in order to make sure that work gets done. And they're the experts on that. I'm looking forward, I'm hoping this summer, to get a chance to sit down when some of the design work is being discussed to learn more about how the design elements would impact the maintenance costs.
And I'm curious too, just as for part of that question, for the multi-benefit projects, what are the are there like cost differences and to those as well?
Well, so here's an interesting thing I learned as part of this project is by setting the levees back and then by excavating between the levees to make side channels or terraces, they may be able to generate what they call borrow material that can be used to construct the new levees. It can actually save
Mm,
money.
mm,
All right. Now, again, it depends. There has to be the right kind of material, the right grain size, so forth. But the cost can actually be a wash or even cheaper, right? Rather than just putting the levee and leaving it all the way it is, because then you'll have to truck in all of that material. And we're talking thousands of truckloads, just a real hassle and a real high millions of dollars. So, in fact, the multi benefit can potentially, again, it really comes down to the design, but it can potentially save money. As far as the maintenance goes, that remains to be determined. If there's a bunch of extra structures, then and they need some maintenance every couple of years, that's going to have a cost. But if in doing that, we're enhancing habitat, improving water quality, and getting more groundwater, then if you look at the cost benefit overall, it may still pencil out. One of the challenges with cost benefit analysis is different people get the costs and the benefit, right? It kind of depends on the footprint you look at. And so that's, again, it's one of these things where in principle, I think it can be positive. It can be net positive, but the benefits and the costs may be distributed differently.
interesting.
Yeah,
There's a lot to analyze there.
there is. These are things I never really thought I would be studying or learning about. But it's necessary because we can't do the work without really thinking about these other pieces.
Hmm. All right. Well, thanks for sharing that. We did have a few more questions, but because of timing, we're going to go to our closing remarks now. So I'm just going to ask everyone, let's have a big round of applause for Professor Fisher. Thank you so much. Thank you
Thank
for
you.
leading us in this great discussion tonight. And if those of you in the audience would like to donate to the Recharge Initiative, you can check out the link in the chat. And Andrew, I don't know if you wanted to talk a little bit more about that, the Recharge Initiative.
I mean, it's a small fund. I use it to support students sometimes and some of our field work. Mostly we're funded pretty well, but especially the next couple of years, we'll see what happens. It's nice to just have a little bit of unrestricted funding that we can use for student support and field work and so forth. The Recharge Initiative was kind of a limb I climbed out on after getting promoted to full professor. And then I wrote up a little manifesto that I put up online. I said, we're going to do this. And here's why we're going to do it. And I'm going to spend the next 20 years doing this. And then I started sawing off the limb. Like it was sort of a way to make me just do it, to not just think, oh, this is something I could do, but like to make me do it. So
Oh, wow.
that's really what it's been. And I partnered with people at different agencies and universities for the work. But if you go to the Recharge Initiative website, you can read the manifesto. I updated it a little bit. It was a little out of date, but I think the last time I updated it was about 8 years ago. And it just says like, this is what we're committed to. And it's really finding where to do recharge, figuring out how to do it better, improving water quality, and creating incentives. And I'm proud of what we've done as a group, like all of us, because we're doing it. We're making it happen. And it's been a lot of work, but it's also been really gratifying. And especially to think that we can be part of a solution. I think we hear a lot of negative stuff in general, and I like doing things that make things better. So I'm
Yeah.
grateful for that opportunity.
Yeah. Well, thank you for sharing that. That's amazing. Um, all right. Well, as Julia mentioned previously, my name is April Yee, and I'm a member of the Alumni Council and one of the volunteer organizers for the Slugs and Steins lecture series. So this talk was recorded and it will appear in a few days on the UCSC Arts Lectures and Entertainment channel on YouTube. I would like to thank the staff of the Alumni Engagement and University Events offices who also helped to organize this webinar. So thank you, Shayna, Diana, Paulina, and Nicole. Also thanks to Mike Reapy and Kelsey Knox, who are also volunteer organizers of this series. So our next Slugs and Steins is on Monday, July 13th with Professor Ida Macias Munoz from the Physical and Biological Sciences Division. And an email will go out next week with the speaker and registration details. So we hope you'll join us for that. And in the meantime, there are plenty of other upcoming events that may interest you. And I'd like to highlight just a few. So on Thursday, June 18th and Saturday, June 27th, the Younger Lagoon Reserve is having tours, and these are free and open to the public. And it says to register, you have to call a phone number, but I'm wondering if there is, okay, there's a website you can go to. June 24th and July 1st, Homer's Odyssey virtual reading group hosted by the UCSC Ancient Studies program and Bookshop Santa Cruz. So Homer's Odyssey is becoming a major motion picture. Whether you like movies or not, this would be a great excuse to read this millennia-old story about a salty war hero who just wants to go home. And then August 14th to 16th is Return to the Redwoods, which is a great event where you can reconnect with friends, family, and fellow alumni as you stay on campus and explore the beauty of UC Santa Cruz. There will be a kickoff party, stars and s'mores, hikes, workshops, and family-friendly activity and fun. So this weekend offers something for everyone. On behalf of the UC Santa Cruz Alumni Association, thank you for joining us tonight, and please come back for our July Slugs and Steins. We'll see you next time. Bye.